Let's begin our second lesson on the discriminant by considering a line and a quadratic. The quadratic is y equals x squared minus 3x plus k. Because its constant term is a variable, we're actually looking at a family of functions, a bunch of different quadratics, each with a different y-intercept, depending on what the value of k is. There's no missing parameter in the equation for the line, though, so the slope of this line is 3, and its y-intercept is at 0, -3. Let's consider what these look like when graphed together. While the line remains unmovable, you can see as I adjust the value of k, I move the quadratic up or down depending on how the value is changed. Right now, there are 2 points of intersection between the quadratic and the line. As I increase the value of k, and therefore the y-intercept of the quadratic, these points of intersection will get closer and closer together until we have one point of intersection when k equals 6. As k continues to increase, we no longer have points of intersection between the parabola and the line. Examining the problem graphically helps us visualize what's going on, but we want to also make sure that we have a good algebraic method of solving this problem. In this scenario, I'm curious to know for what values of k will the line and the quadratic have no points of intersection. If you think back to the graphical example you were just shown, you may already know the answer we're going to build to, but I want to walk through the steps for doing this algebraically. The first step is going to involve setting the two equations equal to one another. We are looking for something related to their point of intersection, so it only makes sense that we set them equal to each other, as if we were solving for the x value. Once we've done this, we'll want to rearrange the equation by moving everything to the left-hand side. Now we are once again in a position where we have a quadratic equation with a missing parameter k that we're going to be able to solve for. Remember here that we're not actually looking to solve for the values of x. In fact, we're looking to solve for a value of k that will create a certain scenario related to the solutions of x, namely that there's one solution, two solutions, or in this particular instance, no solutions. To accomplish this, we are going to need to find the discriminant. So we'll set up our general form for this equation, and then sub in the given values from the quadratic equation we've set up. If we simplify this, we will get that the discriminant is equal to 24 minus 4k. Now we're looking for the values of k that will make it so there are no points of intersection, so we need to find when the discriminant is less than 0. So I'll set 24 minus 4k to be less than 0. Now in this instance, I'm solving a simple linear inequality. So 24 is less than 4k, and that means that k is greater than 6. This is the same result we arrived at when we solved the problem graphically, and so it should come as no surprise that this is the solution we found algebraically as well. The steps that were highlighted in this example will be useful to you when solving any problem that uses the discriminant when dealing with the intersection of two functions. Whether it's a line and a quadratic or two quadratics, the steps that you go through will ultimately be the same. The one thing that will change from question to question will be whether you end up solving a linear inequality, like we did in this example, or a quadratic inequality, like we did in the previous lesson's exercises. Regardless of the circumstances, the skills being applied are the same and the steps being undertaken are the same. So it's important to remember the logical thinking we use in each of these problems so that you can solve them all with success.